Welcome viewers. In this video we will see the design of ripple or synchronous counter. See the first problem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, design of ripple or synchronous counter. The first design is design BCD mod 10 ripple counter using JK flip-flop. So this ripple or asynchronous counter means the operation is not synchronized. Synchronous counter means all the flip-flop given the same clock pulse. We know that counter is made up of flip-flop. All the flip-flop receive the same clock pulse. In asynchronous counter, first flip-flop will receive the clock pulse. Output of first flip-flop is given as a clock pulse to the second flip-flop. So the operation is not synchronized, so that it is called asynchronous. Also called as ripple. Mod 10 counter means 10 outputs will be there. 0 to 9, 10 combination of output will appear. 10 to 15, remaining 6 outputs will not appear. That is called a mod 10 counter, only 10 outputs. For example, mod 5 counter means 5 outputs will be there. Remaining 3 will not available. Total 8 outputs, 5 will be appear, remaining 3 will not appear. Mod 10 mean out of 6, that is 16. 2 to the power 4, 16 combination. 0 to 9 will appear. 10 to 15 will not appear. That is called a mod counter. Similarly, we have mod 5, mod 6, 7, 9, like that. Counters are available. So in this problem, we need to decide mod 10 counter. We are going to use the JK flip-flop. First step, determine the number of flip-flops needed based on the combination. Mod 10 means we need to decide number of flip-flop. The BCD counter goes through 0 to 9, that is 10, total 10, that is from 0 to 9, that is total 10 states are available. So n equal to 10 here, n equal to 10. So 2 to the power n greater than or equal to n. This is the condition. This n is the number of states, this small n is the number of flip-flop. So by satisfying this condition, we can decide the number of flip-flop. So we know that n equal to 10. 10 states are there, 0 to 9. So we know that 10 state mean automatically the 4 digit, 2 to the power 4, 16 combination. So n equal to 4, we'll take n equal to 4. So 2 to the power n greater than or equal to n, that is 2 to the power 4 greater than or equal to 10, that is 16 greater than or equal to 10. Right? 2 to the power 4 is 16. So this condition is satisfied. So we need 4 flip-flops are needed. Right? First step, we need to find number of flip-flop, that is identify from this condition. N is the number of states, small n is the number of flip-flop needed. So now we need 4 flip-flops are needed. The second step is type of flip-flop, which type we are going to use. In this problem itself, it is clearly given JK flip-flop. If it is not given in the problem, we can decide according to our wish. But here it is clearly given JK flip-flop. Now we need to go for the truth table for the counter. That is mod 10 counter. Based on the given problem, we need to identify the truth table. Right. So this is the truth table available. Clock pulse A, B, C, D, 4 digits. We need to find the output of reset logic. Because 0 to 9 we need the output. From 10 to 15 we don't need don't want the output. So we need to reset the flip-flop. So that we need to identify what is the reset logic of Y. So this is 0, clock pulse, 0, 1, 2, up to 9, right? So 0 to 9, 10 combinations are available. So we know that 4 digits are mean 0, 0, 0, 0, 0, 1, 0, 1, 0, like that it will go, right? So up to 0 to 9, we need the output. So this is called a valid states, 0 to 9, 10 combinations are valid state. From 10 to 15, remaining 6 outputs, we are not needed. So we are giving only 10 clock pulse. Thereafter clock pulse is not there. So this combination 10, 11, 12, 13, 14, 15, we don't want the output. So this reset logic is 0. So this is coming under invalid states, right? 0 to 9 valid states, 10 to 15 invalid state. Now we need to find the logical expression for this reset logic so that can be implemented with the logic diagram. Right. Now we'll see the description available here. the reset input clear of each flip-flop is active low input. By making clear input of all flip-flop logic low, we can reset the counter, right? So this is given as a logic low. Thus reset logic is designed such a way that for invalid states y equal to 0, so that the counter will reset, right? If y equal to 0 means it will reset. So after 9 it will reset to 0. Again it will go 0, 1, 2 up to 9, right? So 10, 11, 12 means it will reset. So 0 to 9, after that again it will go to 0. Now we'll see the logical expression for this reset logic y using the Karnaugh map. So this is the Karnaugh map for finding the logical expression of reset logic y, right? There are 4 variables available. We have 4 variable K map A, B, C, D. So D is the MSB, A is the LSB. So that we take D, C available in vertical manner, BA available in horizontal manner. Totally 4 variables. DC 2 variable, 4 combinations. We know that 0, 0, 0, 1, 1, 1, 1, 0. There is a interchange between third row and fourth row. 0, 0 means D dash C dash. 0, 1 means D dash C. 1, 1 means DC. 1, 0 means D C dash, C bar. Similarly, BA 2 variable, 4 combinations 0, 0, 0, 1, 1, 1, 1, 0. So B bar, A bar, B bar A, BA, BA bar, right? Now in this logic we know that this is a min terms 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There is a interchange between third column and fourth column. Similarly, third row and fourth row. We know that it is a mod 10 counter. From 0 to 10, 0 to up to 9, the inputs are 1. This 10, 11, 12, 13, 14, 15 are zeros, right? So by using the min term, we can easily put the 1 as a logic high in this K map. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally 10 outputs are we need. So it is marked as 1. 10, 11, 12, 13, 14, 15 are not needed. These 6 inputs are marked as 0. Now we need to group the cells in order to identify the logical expression. So here the 8 ones are available. So these 8 ones are grouped together. These 2 ones are grouped by top and bottom. These 2 ones and these 2 ones are grouped together. So totally 2 groups are available. Grouping 8 cell, grouping 4 cells. So while grouping these 4 cells, these 8 cell, we need to refer corresponding first row, second row. Similarly, corresponding first column, second column, third column and fourth column. So while referring the first row and second row. So while referring first row and second row, D bar, C bar, here D bar, C. So C bar got cancelled. Only D bar is available. Right, that is written here. What about these columns? All are cancelled. B bar, A bar cancelled by BA. B bar, A cancelled by BA bar. Right? So all these 4 terms are cancelled. Only these 2 terms. In that C dash also cancelled. C dash. So that only we got D dash, D bar. Right. Now we'll see grouping of these 4 cells. We have to refer the corresponding first row and fourth row. Similarly, first column and second column. First we will refer the first row and last row. D bar, C bar. D, C bar. So C bar is available commonly. D bar, D got cancelled. Only C bar. The C bar is written. Now we have to refer the first column and second column. B bar is available commonly. A bar, A got cancelled. So B bar. So grouping these 4 cells, we got C bar, B bar. So the reset logic y equal to D bar plus C bar into B bar. So to implement this, what we need is, we need one OR gate. For this C bar and D bar, we need one AND gate. AND gate will multiply C bar and D bar. By using one more OR gate, we can add these 2 terms. That is given as a reset of the 4 flip-flop. So that it will go from 0 to 9. When it goes to 10, it will reset the flip-flop. Again, it will start the 0. Now we'll see the logic diagram. So this is the logic diagram. So the four, we already decided the four flip-flops are needed. A, B, C, D. So this is the output. A, B, C, D. MSB. D is MSB. A is LSB. Right? We are already know that JK flip-flop we are using. JK. So all this flip-flop is given logic 1, logic high. High input is given for the all flip-flop. J as well as K. JA, KA, JB, KB, everything receive the high output. Logical high output is given to the all four JK flip-flop. What is the nature if the JK, J and as well as K receive the high input? It will toggle. The output will toggle. 0 means it will goes to 1. 1 means it will goes to 0. We know that we have present state and next state. Present state 0 means it will go to 1. Present state 1 means it will go to 0. If both the inputs are 1. We know that both the inputs are 0 means no change. If K equal to 1 means reset 0. J equal to 1 means set 1. Both are 1 means toggle. Right? So all the four flip-flop JK type is given with high input. Both J and K receive the logic high. So every clock pulse the output will toggle. So we will verify with the output. And another thing is only this first flip-flop receive the clock pulse. Second flip-flop, first flip-flop output is the clock pulse of second flip-flop. Second flip-flop output is clock pulse of third flip-flop. Third flip-flop output is clock pulse of fourth flip-flop. Right? So this flip-flop will toggle with every clock signal. This flip-flop will toggle based on the A value. If A is 0, there is no change. If A is 1, it will toggle. And also here inverter is there. So A is 0 means it will toggle, 1 means it will not toggle. 0 means while giving it become 1, so it will toggle. 1 means it will not toggle. Similarly there B. Based on the B value, the third flip-flop will toggle. Based on the C value, fourth flip-flop will toggle. Right? So flip-flop A receive clock pulse always. So every clock pulse the output toggles. B, C, D flip-flop based on the output. This B flip-flop based on the output of A it will toggle. Similarly C based on the output of B. D based on the output of C. Right. Now we have the reset logic. Here the clear signal is available. This is also inverted. Right. So we already know that Y equal to D bar plus C bar B bar. Right. So C bar into B bar we have one AND gate is available. So C bar is connected and B bar is connected. So it will give C bar into B bar. That is connected to OR gate with another input D bar. So this is nothing but D bar plus C bar B bar. This OR gate will produce the reset logic Y. That is nothing but D bar plus C bar B bar. That is given to the reset clear button of all the four flip-flop. So what is the reset logic? 0 to 9 it will give the signal. Thereafter it will reset. So that flip-flop again reset, it will start from 0 to 9. 10 means again it will goes to 0 to 9. Right. So this is the logic, so that we will get the 0 to 9 mod 10 counter. So in this video we discuss design of ripple or asynchronous counter, mod 10 counter. Out of 16 outputs, only 10 outputs will be available, remaining 6 outputs are not available. So that is decided by the truth table by reset logic. We design the reset logic. Truth table is given 0 to 9, 1, 10 to 15, 0. So based on that, by using K-map, we got the logical expression Y, and that is implemented with the logic diagram. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the design of ripple or asynchronous counter, design 3. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, ripple or asynchronous counter design. We know that counter is made up of flip-flop. Flip-flop is the storage element. Asynchronous counter means the clock signal given to the first flip-flop output of first flip-flop is given to the clock pulse of the second flip-flop. Like that it is connected. So the operation is not synchronized, so that is called a asynchronous counter. Synchronous counter means all the flip-flop receive the same clock pulse. In this we are going to see the design mod 6 ripple counter using T flip-flop. So what is mod 6 counter? There are 6 outputs will be there. Remaining outputs are disabled. That's called mod 6. Mod 5 means 5 outputs will be there. For example, mod 6 means definitely we need 3 bit, 2 to the power 3, 8 outputs are there. So only 6 outputs will be available, 7 and 8 output will be disabled. That is called a mod counter. So clearly here given, we need to use the T flip-flop. Right. The step 1 will determine the number of flip-flop required. Here the counter goes from 0 to 5. That is, total 6 states are available. 0 to 5 state means 6 states are available. That is n, capital N equal to 6. So the number of state is 6, n equal to capital N equal to 6. In order to find the number of flip-flop, the condition is 2 to the power n greater than or equal to n. 2 to the power small n greater than or equal to n. So this n is nothing but the number of flip-flop. I will take n equal to 3. So 2 to the power 3 greater than or equal to 6, that is 8 greater than or equal to 6. So this condition is satisfied. So 3 flip-flops are required. Right? So n equal to 3 while substituting, this condition is satisfied. So we identified that there are 3 flip-flops are needed. Next we need to find the types of flip-flop. So in this problem itself it is clearly given T-type flip-flop. If it is not mentioned, we can use any type of flip-flop. Now we'll see the truth table based on the design given. Mod 6 ripple, based on that we'll see what is the truth table for this mod 6 counter. So this is a truth table available. So clock pulse CBA. So A is the LSB, C is the MSB. So these are all 8 possibilities are available. 3 bits, 2 to the power 3, 8 possibilities. In that we need only 0 to 5, mod 6. 6 outputs are needed. 7 and 8 should be disabled. Only we need 0 to 5. Again we start from 0. 0, 1, 2, 3, 4, 5. Again it goes to 0. 7 and 8 is disabled. So that is done by the output of reset logic. After 5, we need to reset the flip-flop so that it will go to the 0. Right? So we can use reset logic in that from 0 to 5. First 6 states it is 1. For 7 and 8 is 0. When it is 7 and 8, it should reset to 0. So that the flip-flop will go from 0 to 5, 6 state. Again it will go to 0. 7 and 8 will not appear. So this is the valid states, 0 to 5. 7 and 8 is invalid state, 0. So this signal we are going to give as a clear signal of the flip-flop, so that it will clear the output up to 5. After that up to 5 it will give the output. 7 and 8 it will clear the output, and again it will goes to 0. Now we need to find the logical expression for this reset logic. So by using the Carnap map, by using K map we can find. So step 4 is reset logic expression. So this is a 3 variable K map. C is available vertically, BA available horizontally. C 1 variable, 2 possibilities, 0, 1, C bar C. BA 2 variable, 4 possibilities, 0, 0, 0, 1, 1, 1, 1, 0. B bar A bar, B bar A, BA, BA bar. We know that this is a min term, 0, 1, 2, 3, 4, 5, 6, 7. So in that 0, 1, 2, 3, 4, 5 are needed. 6 and 7 is 0. So what is available here? It is mapped. Now we need to group these cells. So there are 2 grouping. These 4 cells are grouped together, and these 4 cells are grouped together. So while grouping these 4 cells, we have to refer the corresponding row. It is C bar. In the corresponding column, we have to refer. All 4 columns are covered. But B bar, A bar cancelled by BA. B bar cancelled by B, A bar cancelled by A. B bar A cancelled by BA bar. Here B bar cancelled by B, A cancelled by A bar. So all are cancelled. Only C bar will be there. While grouping these 4 cells, we have to refer the corresponding first row and second row. First row C bar, second row C. So C bar got cancelled. Similarly, we have to refer first column and second column. B bar, A bar, B bar, A. So A bar, A cancelled. B bar is commonly available. So the resultant is B bar. So the reset logic Y equal to C bar plus B bar. So here we need one OR gate. In that one input is C bar, another input is B bar. So that is given as a clear input of the all flip-flop. So that it will clear up to 5, it will execute. After that it will reset the flip-flop. Now we'll see the logic diagram. We need to implement Y equal to C bar plus B bar. So step 5 is the logic diagram. So this is a logic diagram available. So we need 3 flip-flops. T-type 3 flip-flop available. A, B, C. C is the MSB, A is the LSB. The output is A, B, C is the output. What we discussed already. C, B, A. The logic high is given to all the flip-flop. The T flip-flop receive logic 1. High input is given to T flip-flop. What is the nature of T flip-flop? If the input, logic input is high, the output will be toggle. Right? 0, the present state, next state. We know that present state, next state. Present state 0 means it will toggle to 1. Present state 1 means it will toggle to 0. That is the nature of T flip-flop while receiving the logic high. If the logic low means no change in the present state and next state. But here every clock will receive the high output, logic high input. So output will toggle for every clock pulse. Every clock pulse, the output, the present state is toggle. What about this flip-flop B? So this flip-flop A only receive the clock pulse because of asynchronous counter. Flip-flop B is clock pulse is nothing but output of first flip-flop is the clock pulse to the second flip-flop. Similarly, output of second flip-flop is clock pulse to the third flip-flop. So this flip-flop will toggle based on the every clock pulse. This flip-flop will toggle based on the A value. A value it will toggle. For example, A equal to 0, we are applying the inverter. 0 means 1 is applied, so it will toggle. If A equal to 1, it will not toggle. Same state will be maintained because of inverter. Here also, during every trailing edge, we have positive edge and negative edge. During negative edge, this output is toggle. Similarly, during this negative edge, B is toggle. Similarly, during the negative edge, C will toggle. So A based on clock pulse, B based on output A, C based on output B. So this flip-flop is working. So the clear signal is there because we need only 6 outputs. 7 and 8 should be resetted. So that's done by this logic OR gate. We already discussed that Y equal to C bar plus B bar. So this OR gate we are using, this B bar is connected. This is B bar, complement. Similarly, C bar is connected. So this Y equal to C bar plus B bar, that is given to the clear signal. So what will happen? Reset logic is designed such a way that for a invalid state, Y equal to 0 and counter restarts. So it will execute 0 to 5. If 6 and 7, it will reset. So again it will start to 0. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the design of ripple or asynchronous counter design 2. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Design of ripple or asynchronous counter. Second design. Design a 3-bit asynchronous ripple counter using T flip-flop. We need to design the 3-bit asynchronous ripple counter using the T flip-flop. So we know that counter is here counting from 0 to n or n to 0. It is made up of flip-flops. This asynchronous or ripple means in this asynchronous counter, the flip-flop, first flip-flop will receive the clock pulse. Remaining flip-flop, the output of one flip-flop is given as a clock signal to the next flip-flop. So the operation is asynchronous. Synchronous means all the flip-flop will receive the same clock pulse, right? So the T flip-flop we are going to use. The diagram shows the 3-bit asynchronous ripple counter using the T flip-flop. So it is clearly given there is 3-bit asynchronous counter. So we need 3 T flip-flops are used. A, B, C. C is the MSB, A is the LSB. What is the nature of the T flip-flop? If the T input is 1, the output will toggle. If T input is 0, no change in the output. Present state and next state. We know that in flip-flop we have present state and next state. If T is 0, present state and next state both are same, no change. If T input is 1, the present state will change to toggle. 0 means 1, it will 1 mean it will change to 0. Right. So the clock pulse is given here. For the first flip-flop, the clock pulse is given. And also the input for all the flip-flop is logic 1. So 1 is given. So what happened? 1 means the output will toggle. So every clock pulse, the output will toggle for a flip-flop A, because clock pulse is given and also given logic 1. So every clock pulse, the output will toggle from 0 to 1, 1 to 0. The second flip-flop also logic 1, but the clock pulse is QA is the clock pulse of the second flip-flop, and also it is inverted, negative edge. So if QA is 0, 0 means 1 is applied. So if it is QA is 0, the output will toggle. If QA is 1, 1 means 0 is applied, so no change, right? QA 0 means QB will toggle. QA 1 means QB will not toggle. Same state will maintain. Similarly, C also. High output is given. QB is 0, QC will toggle. QB is 1 means no change in the QC. So this is the nature of this asynchronous using the T flip-flop. Now we'll see the clock diagram so that we can see whether we are getting 3-bit binary output. As shown in the diagram, the clock input of only first stage of flip-flop. The clock input of second stage of flip-flop is triggered by first flip-flop output QA. First flip-flop output QA is given as a second flip-flop clock pulse. Similarly, third flip-flop is triggered by second flip-flop output QB. Right. Since T input is connected to logic 1, each flip-flop toggle at clock input. That is the nature. If the T input is 1, every clock pulse, the output will toggle. Now we'll see the clock diagram and the 3-bit output. 3 means 2 to the power 3. There are 8 outputs will be there, 0 to 7. So this is the clock pulse. So the 3-bit counter, this is 3-bit asynchronous counter, 2 to the power 3, 8 states are available. So 8 clock pulse we are referring. And this is the QA. Initially all are 0. QA, QB, QC all are 0. It is reset to 0. So we already discussed this clock pulse is given to the first flip-flop. So whenever the clock pulse, that is negative edge, the clock pulse is inverted, clock pulse is given. This is called positive edge, changing from 0 to 1, high level, low level to high level. But here we are giving invert. When the clock pulse going from high to low during this edge, this is called positive edge, this is called negative edge. So during every negative edge, the output of T flip-flop will toggle, right? So if the clock pulse is directly given, that is called positive edge. During every rising edge, the flip-flop will toggle. Here given inverted, so during every negative edge, trailing edge, the flip-flop will toggle. So initially 0. So during this negative edge, 0 is changed to 1. This is positive edge. We have to refer only this negative edge. Again during this negative edge, 1 is changed to 0. Again at the end of this negative edge, 0 to 1. Right. So this due to inverter, during this every trailing edge, the output of flip-flop will toggle. Right. So see here at this 0 changed to 1. At this 1 changed to 0. Here 0 changed to 1, like that it goes. What about the second flip-flop? The first flip-flop output is given as a second flip-flop clock pulse. That also inverted. So whenever the output of first flip-flop going negative edge, this is negative edge. Similarly, this is negative edge. This is negative edge. This is negative edge. This is positive. Low to high is positive. High to low is negative. So during every negative edge, the second flip-flop will toggle. See here initially 0. Here the 0 will be maintained. Here 1. Here the 1 is given. Here 1, so no change. Here again goes to 0. 0 means changes. 0 to 1 changes. We already know that it is inverted. If 1 is given as a clock pulse, means after inverted it is 0. So no change. If 0 is applied as a clock pulse, inversion, due to inversion, 1 is there. So 1 means it will toggle. Right? During this trailing edge, because of 0 value, 0 is changed to 1. Again here 1, so no change. 1 is maintained. Again here 0, so changed from 1 to 0. Here due to 1, no change. Due to 0 changes, 0 to 1. 1 is maintained. Right? So during every trailing edge, there is a change. Right? What about the third flip-flop? The second flip-flop output QB is given as a clock pulse to the third flip-flop. So during this trailing edge, negative edge, the flip-flop will toggle. Right? So 0, 0, so no change. Here 1, so there no change. Here 0 is there. 0 means 1 is applied, so there is a change. So that 0 is changed to 1 until the next trailing edge. So same 1 is maintained. Right? So due to 0, no change. Due to 1, no change. Here 0 is there. So this 0 means 1 is applied. So the state is changes. T flip-flop state changes. Otherwise, during every trailing edge, there is a change. During positive edge, no change. Now you can see that this is the LSB and this is MSB. Right? 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. So we got the 8 combination of output. 3-bit asynchronous counter, 8 outputs are available. Right? Again after this 8, again it will reset to 0. Right? So I will explain again. The first flip-flop based on the clock pulse. So during every trailing edge, because inverted clock pulse is given, so during every trailing edge, the state is changes. Second flip-flop based on the output of first flip-flop. So whenever the first flip-flop output goes to trailing, that is high to low, the state changes. Here 0 changed to 1. Here 1 changed to 0. Third flip-flop output is second flip-flop output is given as a clock pulse. So whenever there is a negative edge of second flip-flop output, third flip-flop output will toggle 0 to 1. Accordingly, we got this 8 different combination of output as a 3-bit asynchronous counter. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the design of ripple or asynchronous counter design 4. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Design of ripple or asynchronous counter. We know that counter is a digital device is made up of flip-flop that will store the 1-bit data. We have two types, asynchronous and synchronous. Synchronous means all the flip-flop receive the same clock pulse. Asynchronous means first flip-flop receive the clock pulse. The output of first flip-flop is given as a clock pulse to the second flip-flop. So the second flip-flop operation based on the first flip-flop. So the operation is not synchronized. So that is called a asynchronous counter. It is also called as a ripple counter. Now we'll see the design. Design the ripple counter for the state diagram shown below. Based on the state diagram, we need to design the ripple counter. So it is from this is state different. There are 5 states available. 1, 1, 1 changed to 1, 1, 0. Then it goes to 1, 0, 1, 1, 0, 0, 0, 1, 1. Right? So the 3 digits available. So definitely there are 8 8 states will be there, but only 5 states are here we needed. Remaining 3 states is not needed. And also it is clear that this is a down counter. You start from 111, is keep on reducing 110, 101, 11, 100, 011, right? So this is the 3-bit counter. 8 states are there, but in the state diagram only 5 states available. Remaining 3 states we need to disable, and also it is coming under the down counter. So based on that we can see the step 1, determine the number of flip-flops. So n equal to 8. We know that this 3 digits are there. So definitely n equal to 8. There are total 8 states will be there. So 2 to the power n greater than or equal to n. So that is the condition required. Based on the condition we need to identify the number of flip-flop. If n equal to 3, we will take n equal to 3. 2 to the power 3 greater than or equal to 8. So that is 8 greater than or equal to 8. So this condition is satisfied. So we need 3 flip-flops are needed. So totally 8 states will be there. But in that we are going to use only 5 states. Right. So here we can take n equal to 5 also. What we need is n equal to 5. So that 2 to the power 3 is, this will be 5. So for that case also this condition is satisfied. Right, total 8 states, but in this state diagram only 5 states are there. So we will take capital N equal to 5. So based on this condition, 8 greater than or equal to 5. So this condition is satisfied. So we need 3 flip-flops are needed. The second one is we need to find the what type of flip-flop we are going to use. So here we will going to use the JK flip-flop. Any type of flip-flop can be used, but in this we are going to use the JK flip-flop. Now we'll see the truth table. Based on the state diagram, we need to design the truth table. So this is the clock pulse available. C, B, A. C is the MSB, A is the LSB. Right? It's a down counter, so it is written in reverse order. N to 0. 111, 110 up to 000. So normally we'll write from 0 to n, here n to 0. So in this the first 5 states are needed based on the state diagram. So the first 5 states are 1, 2, 3, 4, 5 are 1, remainings are 0. That is, this is a preset logic. We need to preset the flip-flop so that it will execute from 0 to 4, 5, 6, 7 minutes it will preset. Again it will start. If it is up counter, we will give the reset logic. 0 to 5, thereafter the flip-flop will be reset. But because of down counter, because of up counter, we are using the preset logic, right? So up counter we are using reset logic, down counter we need to use the preset logic, so that the preset, the flip-flop will be preset. Again it start goes from the high level. So for the based on the state diagram, first 5 are high, remaining 3 are low. It is also, we can take it as mod 5 counter. Right. So it is clear that up counter we are using reset, down counter we are going to use the preset. Now we need to find the logical expression for this y, so that we can give this preset. For that we are going to use the Karnaugh map. There are 3 variables. This is a 3 variable K map. C is represented in vertically, BA represented horizontally. C 1 variable, 2 possibilities, 0, 1, C bar C. BA 2 variables, 4 possibilities, 0, 0, 0, 1, 1, 1, 1, 0. B bar A bar, B bar A, BA, BA bar. Now we need to fill the columns. So it is from 0, 1, 2 is logical low. 3, 4, 5, 6, 7 logical high. So we know that these min terms are, if we represent min term, this is 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2 is logical low, 0, 1, 2. 3, 4, 5, 6, 7 is logical high. Right? So that totally 5 states will be there. So now we need to group this. So these 4 cells are grouped together. These 2 cells are grouped together. While grouping these 4 cells, we have to refer the corresponding second row. Second row is C. Similarly, corresponding columns. All 4 columns are covered. So B bar, A bar cancelled by BA. B bar A cancelled by BA bar. So all are cancelled. Only C is there. While grouping these 2 cells, we have to refer the corresponding first row as well as second row. First row, second row, C bar C is there. Got cancelled. The corresponding column, third column, BA. So only BA. This row cancel, only column is there, BA. So Y equal to C plus BA. Since it is down counter, we need to derive the preset logic instead of reset logic. Right? Up counter means we are using reset logic. Down counter we are using preset logic. So that it will go from this 0, 1, 2, it will not execute. 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, it will execute because of preset logic. Now we'll see the logic diagram. Based on the design, we'll go for the logic diagram. So we already discussed there are 3 flip-flops are needed. A, B, C. We are using JK flip-flop. The logic high is given to J input as well as K input. J also logical high, K also logical high. All 3 flip-flop receive the logic 1 as a input. Then what is the nature of JK flip-flop? If both the inputs are high, the output will toggle. The output, this present state and next state will toggle. Present state 0 means next state will be 1. Present state 1 means next state will 0. So this A will toggle. This is the output for every clock pulse, because this is given as a inverter. So during every negative edge, this output will toggle. During positive edge, it will not toggle. What is positive edge and negative edge? So this is the clock pulse. This is positive edge, changing from 0 to 1. This is negative edge, 1 to 0. So during every negative edge of the clock pulse, this flip-flop will toggle because of both are high. What about the second flip-flop? The clock pulse to the second flip-flop is A bar is given as a clock pulse. If A is given as a clock pulse, there is a up counter, right? Because this is down counter, so that A bar is given, right? A given means up counter, A bar given means down counter. So during this the negative edge of this A bar, this B will changes. B will toggle for every negative edge of A bar. Similarly, this third clock pulse third flip-flop will receive the clock pulse from B bar, right? So every negative edge of B bar, C will toggle. So that this first flip-flop depends upon clock pulse, second flip-flop output depends upon A bar, third flip-flop output C depends upon B bar. So the operation is not synchronized, so that it is called a asynchronous counter. So every negative edge of this clock pulse, the output of the first flip-flop A will toggle. Every negative edge of the A bar, first flip-flop output A bar, the second flip-flop output B will toggle. Similarly, every negative edge of B bar, C will toggle. Now because of down counter, we are using the preset. Preset also logical low. We need to give the preset logic based on the expression what we discussed. C plus AB. That is the preset logic we obtain from the K-map. So C plus AB, we need one OR gate. C is connected. A into B, we need one more AND gate. So A and B is connected. So here AB will come. So AB plus C done by OR gate, that is given as a preset logic. So from the 7 to 4, it will execute. 5, 6, 7, that is the clock pulse, that is 0, 1, 2. These 3 will be preset. So it will go for the down counter, start from the 7, 6, 5, 4, 3. Thereafter it will reset, right? First 5 states will be executed, remaining 3 states will be preset. So in this video we discussed the design of ripple counter using the state diagram. In the state diagram, 5 states are there, and also we can 3 digits, and it's coming under down counter. So we discussed, based on the condition, we decided 3 flip-flops are needed. Then we discussed the truth table. What the given 5 states are 1, remaining states are 0. Based on that, we obtain the logical expression for preset because of down count. That preset is implemented in the logic gate. We are using JK flip-flop. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.